And welcome back as we continue our cosmic journey in astronomy. We're now going to go ahead and take a look at how we can use spectroscopy in astronomy. So previously we had, of course, talked about electromagnetic radiation. As we might know, electromagnetic radiation carries a lot of information about the natures of stars and other astronomical objects. So if we want to extract this information, astronomers first have to be able to study the amounts of energy we receive at the different wavelengths of light in fine detail. And that means we have to really kind of examine those properties of light. If you remember, we did establish previously that light has two main things. It can act as a wave or it can act as a particle. And the way these behaviors are, they're very important to the design of the telescopes and other instruments that we're going to use when we're trying to make these determinations. First off, light can be reflected from a surface. If the surface, for example, is smooth and shiny, such as with a mirror, then the direction of the reflected light beam can be calculated accurately from the knowledge of the shape of the reflecting surface. Light can also be bent or refracted when it passes from one kind of transparent material into another. So, for example, when it's passing from air into water, you'll see a refraction. Now, reflection and refraction of light are the basic properties that make possible pretty much all of our optical instruments that we have, anything from eyeglasses to giant telescopes that we have. Now, such instruments are generally combinations of either glass lenses, which bend light according to the principles of refraction, and curved mirrors, which depend on the properties of reflection. So, let's go ahead and first start by looking at this through the light in a prism. Sir Isaac Newton in 1672 had submitted a paper to the Royal Society in which he described how sunlight can pass through a small hole and then through a prism. And when it does this, he found that sunlight, which appears to be pretty white to us, is actually a mixture of all the different colors that are in the rainbow. When sunlight passes a beam of white light through that prism, we can see a rainbow colored band of light that we can call a continuous spectrum. As we see here, you can see it's one color all the way going right into another. There's no really kind of end to that spectrum. You don't have necessarily distinct points in it. It doesn't like red hard stops and then you have an orange hard stop. Instead, it seems to more blend through this color spectrum. And so light actually has some dispersion properties that we can look at then. So light is separated into different colors with a prism. Upon you entering the prism, that light that you have shining in there is going to actually be refracted or bent. And one of the things to note is that the colors that are bent are not all necessarily bent by the same amount. The bending of the beam is very dependent on the wavelength of light that is passing in, as well as the properties of whatever material you're shining it into. And as a result, you can get different wavelengths or colors of light that are bent by different amounts, and therefore can follow slightly different paths through that prism. This phenomenon of the light bending and just going through to its different paths based on wavelength is dispersion, and really kind of explains Newton's rainbow experiment. Now, upon leaving the opposite face of the prism, light is bent again and further dispersed. If the light leaving the prism is focused on a screen, for example, the different wavelengths or colors that make up the white light are lined up just pretty much like a rainbow, the classic RGB. Now, because this array of colors is a spectrum of light, it's not, again, we don't have hard lines defining where one color ends. The instrument used to disperse the light and form the spectrum is called a spectrometer. So here's another closer look at a more continuous spectrum. When white light passes through a prism, it is dispersed and forms a continuous spectrum of all the colors. Now, although it's hard to see in this version that we have here in our image, it's actually a very well dispersed spectrum, and you have many subtle gradations in color, such as the one end to the other, from the violet to the red. So if you look here, you can see in this image representation how the colors, again, they kind of blend gradually from one to the other. And of course, we have our shorter wavelengths here to our longer wavelengths down here. Reds, of course, being here these longer wavelengths, and the shorter wavelengths being here for ultraviolet. And remember, this is just one part of this continuous spectrum that we are looking at. Now, what value does this have for looking at this with the cosmos? So if we were to say, okay, let's look at this spectrum, but through the cosmic lens, what are we going to use it for? Well, when Newton described the laws of refraction dispersion in the various optics that he was using, and then he observed the solar spectrum from our own sun, all he could see at that time was just a continuous band of colors. Now, if the spectrum of the white light from the sun and stars were simply just a continuous rainbow, astronomers would have very little interest in the detailed study of a star spectrum once they had learned its average temperature. In 1802, however, William Wollaston built an improved spectrometer that included a lens to focus the sun spectrum on a screen. Remember, we talked about how you can put it on there and see the rainbow. With this device, he was able to see an interesting thing, that colors were not actually spread out uniformly, but instead there were some ranges of colors that were missing, and these ranges actually appeared as dark bands within the solar spectrum. And then in 1815, German physicist Joseph Fraunhofer, upon a more careful examination of the solar spectrum, found about 600 such dark lines, which kind of led scientists rule out the boundary hypothesis. Up to this point, they figured, red had a stopping point, blues had a stopping point, but once they started doing some of these experiments, they realized these boundaries aren't necessarily so hard and fast. So, for example, we start looking at the visible spectrum of our sun. You can see that in this representation here, our star spectrum is crossed by dark lines produced by atoms in the solar atmosphere that absorbs light at certain wavelengths. Researchers found that similar dark lines can be produced in the spectrum of artificial light sources. So, for example, if you have a lamp or a candle or something like that, you can get similar things to happen. And they did this by passing their light through various apparently transparent substances, usually containers with just a thin bit of gas in them. So what did these gases do when we were trying to analyze the spectrum? Well, these gases turned out not to be transparent at all colors. They were actually quite opaque at a few sharply defined wavelengths. Something in each gas had to be absorbing just a few colors of light and none of the others. Now, all the gases did this, whether they were testing air, oxygen, hydrogen, whatever, but each showed a different element absorbed a different set of colors, and therefore it gave us different dark lines. So if the gas and container consisted, of two elements, let's say oxygen and maybe carbon dioxide, then passing light through it was missing those appropriate colors, showing the dark lines for both elements. So it became clear that certain lines in the spectrum go with certain elements. And so here is another example of a continuous spectrum and line spectrum of different elements. We have sodium, we have hydrogen, calcium, and mercury. When one gas was set to be pure hydrogen, you would get one pattern of colors. When it was pure sodium, you get a different pattern. Now, a mixture of hydrogen and sodium emitted both sets of spectral lines. So the colors of the gases that were emitted were the same as the colors when it was a continuous source of light behind them. So let's kind of picture these lines here. All right, so this is sodium, this is hydrogen. So they're mixing these together, and we're going to get both of these sets of spectral lines coming through. And from such experiments, scientists began to see distinctive substances show their distinctive spectral signatures when their presence could be detected. And this unique pattern of colors for each type of atom or its spectrum can help us identify which element or elements are in a particular gas. And so these types of spectra are very important for us because ultimately they found about three different types of spectra. The first was a continuous spectrum, which is formed when a solid or very dense gas gives off radiation, and it's an array of all wavelengths or colors of the rainbow. A continuous spectrum can serve as a backdrop from which the atoms of a much less gas can absorb light. You can get a dark line, or an absorption spectrum, which consists of a series or pattern of dark lines, so those missing colors that we talked about, superimposed upon the continuous spectrum of a source. And lastly, we can get a bright line, or an emission spectrum, which appears as a pattern or series of bright lines, and it consists of light which only appears in certain discrete wavelengths. And so these spectral signatures were very, very useful to astronomers. When we have a hot, thin gas, each chemical element or compound can produce its own characteristic pattern of spectral lines, its spectral signature. No two types of atoms or molecules give the same wavelengths. In other words, each gas can absorb or emit only certain wavelengths of the light particular to that gas. In contrast, absorption spectra occur when passing light through a cool or thin gas. The temperature and other conditions determine whether the lines are bright or dark, whether light is absorbed or emitted, but the wavelengths of the lines in any element are the same in either case. Liquids and solids can also generate spectral lines or bands, but because of the nature of liquids and solids, they are broader and less well defined, and hence more difficult to interpret. So we really like gases for this reason. And so that allows us to complete our analysis of spectra. The dark lines in the solar spectrum give evidence of certain chemical elements between us and the sun, absorbing those waves of sunlight. And because the space between us and the sun is relatively empty, astronomers realize that the atoms doing the absorbing must be in a thin atmosphere of cooler gas around the sun. Similarly, we can use the presence of absorption and emission lines to analyze the composition of other stars and clouds of gas in space. And that's really, really helpful, because if we were to take these instruments, use the same spectrum analysis, we can start looking at other stars and seeing what their composition is. So encoded in the electromagnetic radiation that we are receiving from celestial objects is very clear information about the chemical makeup of these objects. And only by understanding what the stars were made of could astronomers begin to form theories about what actually made these stars shine and how they actually evolved and came to be in our celestial sphere. And so that allowed us to, first off, by looking at identifying elements that were in the sun. In 1860, German physicist Gustav Kirchhoff became the first person to use spectroscopy to identify an element in the sun when he found the spectral signature of sodium gas. In the years that followed, astronomers have found many other chemical elements in the sun and stars. In fact, the element helium was found first in the sun from its spectrum and only later identified on Earth. So you might be wondering, though, why there are specific lines for each element. Well, the answer to that is not something that was really kind of found later into the 20th century, and it required really our development of the model for our atoms that we now know and study.